So let's go ahead and look at a numerical solution. There is a numerical model that is a nonlinear model that's described in Appendix G that I'm not going to reproduce here because we'll just focus on the physics again. This is the forcing function that is used to force the waves, and we will do ray tracing given this forcing, which has got a spatial and a temporal structure, which is described this way. We looked at a similar forcing before for the equatorial Kelvin and Rossby waves back in chapter 6. So that was the small scale forcing we had seen before. Here we are changing also to a large scale forcing with this distribution over time. The forcing is initiated. This is the amplitude of the geopotential. So you somehow create doming of the geopotential and you let it go. So that happens ramped up over a few days and then allowed to decay over a few days. So that's the temporal structure. And when you do numerical integration, you look at the solution averaged over this period after the waves have been forced and they are just propagating through the system. Okay. Essentially at that point you think of them as free waves, as I said way back in chapter 4. Typically during an El Nino, for example, there is a westerly wind burst which sets off Kelvin wave and Rossby waves. The wind burst lasts for let's say a week or so, which is enough to project onto these waves, and then the waves, the wind dies away and the waves propagate. We can think of them as free waves at that point. So looking at the perturbation kinetic energy in terms of meters squared per second squared forced at different longitudes, shown here at 90 degree east, 150 degree east, 150 degree west, and 90 degree west in the basic state that is given here up here. So you can see the basic state is varying this way, which is made much more realistic. Since it's a numerical integration, you can prescribe a full field in this case, right? So with the small scale forcing and with the large scale forcing, the amplitude of the trapping or the accumulation of energy at these longitude bands changes, but essentially the trapping happens at the same bands. So even by adding full nonlinearities, given the basic state, the trapping latitudes, longitudes are determined by this basic state, and the forcing, the scale of the forcing, amplitude of the forcing, only changes the amount of energy accumulated, and then we have to see how this energy is radiated out. Okay, and this you can also think of as seasonal changes. For example, an El Nino starts in, let's say, March, April, May, goes through summer, it's fall, and then peaks in the winter, boreal winter, and the seasonal state changes during that time. So those kind of changes can be seen as these basic state changes. And the main message is that nonlinearities, numerical solutions just add more modes to the solution, whereas we have been looking at just k equals -3, k equals -7, and so on. We've been choosing individual wave numbers and individual modes, n equal 1 and so on. Whereas here this is solving the full equations numerically, but the basic story doesn't change, but you can see the large scale forcing produces much more of energy, perturbation kinetic energy, than the small scale forcing. So the scale of the forcing matters as well, because the original waves that are emanating will have different wave numbers, hence different length scales and group velocities. Okay. Looking at it much more realistically, this is now again the easterly regime, westerly regime, and easterly regime, as we saw, with realistic mid-latitude westerlies prescribed in the numerical solution. This is again numerical solution, and you can see clearly the longitudinal variation of the basic flow and the meridional shear in this case as well. Okay, what else can I say about it? Okay, that's about it. The contours here are what are the contours? Okay, the contours are divergence, which I should have read up. It's mentioned right there. So you can use your Coriolis for easterly and westerly flows and figure out convergence and divergence, right? So those correspond to the contours. And as we saw before, in the westerly regime, energy can radiate out much further because the trapping is weakened. Beta effect is weakened, whereas in the easterly regime for Rossby waves and mixed Rossby gravity waves, we know that the trapping effect gets stronger and beta effect is strengthened as well. So that's what is seen in the solution here with the same forcing. So you can see now the forcing at 60 degree east, various days, day 1, day 3, and so on out to day 19. You remember the solution we saw before in chapter 5, I think. You have a eastward propagating Kelvin wave with its perturbation velocities, westward propagating Rossby wave with its structure that is of equatorial, and the Kelvin wave obviously travels much faster and it's trapped close to the equator, but when it hits the basic flows, it begins to have interactions, plus it's also now interacting with the Rossby wave. So the Rossby wave, you can see, is propagated westward, coming back out here and then propagating westward still, and the Kelvin wave that's propagating eastward is going to meet the westward propagating Rossby wave. In the ocean we have boundaries, so as we saw, the eastern boundary reflection and western boundary reflection problems are very different, whereas in the atmosphere waves can go around if they are in a wave number frequency band where they can go untrapped, right? We saw the trapping critical wave number already. So you can see that now the meridional excursion of the wave amplitude is much larger for the Rossby waves already here, and when this interaction happens, you can see that you are now well into the mid-latitudes in terms of the equatorial trapping of the waves. Okay. Differential response as a function of longitude to forcing. This is at 60 degree east, and this is at 1/4. So this is looking at a meridional section at 60 degree east, which is in the Indian Ocean, and 140 degree west, which is in the central eastern Pacific. So you can see that Kelvin wave packets are propagating eastward, and then they meet the Rossby wave that is coming back around. So you had the wave generated here, Rossby wave went westward, Kelvin wave went eastward, and you can see the interaction then expands the energy propagation out towards higher latitudes. That is schematically shown here. Propagation of equatorially trapped modes propagating through a basic flow with latitudinal shear and longitudinal stretching deformation. So the prescribed basic flow has longitudinal variability, which we call stretching, du bar dx less than 0 or greater than 0, so positive stretching or negative stretching, and we have meridional shear. So the basic background flow looks this way. We had easterlies and westerlies. This is called the westerly duct. where the information can propagate much further out in latitude away from the equator. As you can see here, there is a strong meridional shear. This shear here as well, but not as strong as here. Broad arrows denote the relative strength of the flow with the easterlies shaded blue. Okay, and the X indicates the location of the maximum stretching deformation here. So you have maximum westerlies here switching to easterlies. So you have du bar dx having the maximum value here. Characteristics of initially short Rossby waves. So you have eastward group speed, westward phase speed. So you have trapping already happening here. So characteristics of these are Rossby waves and mixed Rossby gravity waves. I don't know why he switched to gravity Rossby waves. Nonetheless, they are usually MRGs, and they get trapped. And the initially long Rossby waves, which have westward phase speed and westward group velocity, have a forward accumulation, so they come back and then they get trapped here. So this is the backward accumulation. So westward phase speed, eastward group velocity, that's why you call it backward accumulation, whereas this is westward phase speed, westward group velocity, and we call it forward accumulation. So that's going to help us in terms of understanding the dynamics as we go into future chapters. Just understand how the waves are interacting with the varying longitudinal flow, and we'll come back to vertical propagation and vertical trapping in a minute.